We will skip this chapter for now. It is more important at this stage to develop a solid understanding of the distinction between the sample of the population, the assumptions for OLS, and the normality assumptions. Of course, I have prepared all the code and course materials, so please use them as needed. Chapter 9. We learned the tools to compare two group averages. We focus on t-test and a few robust alternatives. By the end, we know which test to choose and how much to explain the result. Our aim are for: first, understand independent and dependent t-tests. Second, grasp the intuition behind these tests. Third, know the assumptions. And fourth, practice several tests in R, and we can pick up the right one for our dataset. These are two main situations: independent case and dependent case. Independent case, such as the two different classes case, we use the independent t-test. Second, dependent case, two measures come from the same people, such as before and after. Then we use the dependent t-test, and we can check the statistical significance of the differences. This is the rationale for the t-test. We use the standard error as a gauge of the variability between two means. If the difference between the sample is larger than expected based on the standard error, we have two possibilities: there is no effect, no difference, or there is a differences. The samples are typical of different populations. One is that there is no differences, and two is there is differences. This is evaluated based on the standard error. The impact effect size and standard error size is very important. And this is the formula. The idea is very simple. We compare how big the observed mean difference is to how much random variation we expect between samples. If we observe the gap is much bigger than the expected random noise, we treat it as evidence of a real difference between the populations. If not, we can say that the data are consistent with no difference. Denominator is the standard error. The assumptions for student t-test, standard t-test is here. First is normality. The outcome should be roughly normal in each group. Second, it is measured on an interval scale, and observations should be independent. Finally, the homogeneity of variance is required. When equal variance are doubtful, then we prefer a different version of the test called Welch's t-test. Welch's t-test formula is here. Welch's t-test is more flexible than student t-test. Student t-test is here because these t-tests do not require the fourth one, homogeneity of variance. The important thing is if the variances or sample size is differ, then we should apply the Welch's t-test rather than student t-test. This is the pros and cons of the Welch's t-test. Pros: no homoscedasticity assumptions. This is the biggest pro point. And it also has the sample size flexibility, a good point. It works fine even if you have unequal sample size, like 20 people in one group and 100 people in another. In such case, you can apply the Welch's t-test. Also, third, type 1 error control. It tends to be a bit more conservative than student t-test, which helps avoid false positives. These are the good point, but there is a limitations. First, statistical power is slightly lower than the student t-test, slightly reduced power compared to student t-test. And second, degree of freedom are fractional. Welch's t-test uses approximation, so the degree of freedom can be a non-integer. That can feel awkward to interpret, a bit awkward. And third, normality is still assumed. So if the dataset are highly skewed or the dataset has the heavy tails, then we need to consider another non-parametric alternative methods, such as the Mann-Whitney U test. But basically, the Welch's t-test is more robust than the student t-test in general. Okay, next we analyze a real dataset. I'm not sure real or not, but let's go to the practice session. We will analyze a toy dataset of 24 children. The outcome is mischief score, and the group variable is whether each child has a cloak or no cloak. Cloak means the invisible cloak or no invisible cloak, and they can just mischief or not. Our goal is simply to ask, do mischief scores differ between the cloak group and the no cloak group? Okay, this is the packages. Install packages this, and after that, library. Please do the library command. And if you already installed these packages, you do not need to run again. But I think the WRS2 or some other packages are new for this chapter. Okay, please run these commands. And after that, please install the dataset. Invisibility is read CSV, invisibility.csv, comma header equal to, and invisibility, sorry. Then we can check the dataset. This slide shows how to build a same dataset by hand with the tibble command. Using tibble command, we can create the same dataset like this. But in this case, by this command, you already installed the invisibility dataset, so you do not need to run this command. This is the handmade data creation command, and this is the explanation for that. Okay, so we can skip this slide, and this is the manual handmade code for student t-test. T-test from means equals function blah blah blah. This command shows what the t-test computes. So firstly, you please conduct this command. Then you can understand what is running in the t-test, the automation t-test command, I think. And this is the explanations. It breaks down each line again. For example, the line 1, df equals n1 plus n2 minus 2. It calculates the degree of freedom. This is the degree of freedom. And pool bar this calculates the pooled variance. this is a variance, pooled variance. It's an average of two group variances weighted by their sample size. And third, t equals m1 minus m2 divided by square root pool variance, blah blah blah. This calculates the t statistic. It divides the difference in mean by the standard error. Square root is here. Standard error is this one. This is the t statistics. Mean difference divided by standard error is here. And this is the significance. Line 4. Significance equals 2 multiply parenthesis 1 minus blah blah blah. This calculates the p-value for a two-tails test. And line 5, finally paste 0 blah blah blah. This formats the result into a string for easy reading, rounding the numbers. Finally, the value is rounded to 5 and t value is 3. This is the result part. So firstly, calculate the degree of freedom and the variance, calculate variance. And using this, we calculate the standard error. And using this standard error, we calculate the significance. And finally, we got the result. Okay, next slide. This slide shows the checking the mean standard deviation and sample size n. And this is conducted by group. We use pipe in this in this command. And this is the result of previous operation is passed as the first argument of the next function. This pipe is the one operator and it takes the result of the previous command. And pipe is very many researchers today use the pipe because this is very readable. Okay, and the next step, the first, the group by command, it groups our dataset by the clock variable, clock or no clock. And second, summarize runs the describe command on each of those groups. And finally, unrest wider blah 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 expands the result from the describe function so we can see them clearly in the table. Okay, we can see this one. Here is the output table from the describe command. We can see the two groups, no clock and clock. And we can run the t from means and we use these values here. M1 equals 5, M2 equals 3.75 and standard deviation is here. This is the setting. And this command t from means is here. This is the handmade student t-test command. And this command, this handmade command requires some values. And via this command, we can check n means SD and we use these values here. Then we get the result. This is the handmade command result. And there is the p-value is 0.10. This is the larger than 0.05. So we conclude that there is no significant difference between the two groups. That is the result. Also, we can do this using the existing command. This is very simple. t-test mischief childer clock comma data equal invisibility. Mischief variable to be tested. Clock variable of the group to be divided. And data equal dataset. This is a command, and it is, I think it is the same. Sorry, this is not same because this is conducted by Welch's t-test. The default of the t-test command is Welch's t-test, and if we set the option variance is not equal, then we get that student t-test. But the default case, we do not specify any variance, then Welch's t-test would be done by the command. Okay, we can check this by using our own R. This is the chapter 9. And firstly, install packages. We can ignore the motion library command. Install dataset and check the dataset invisibility. Also, add invisibility. Then we can check first 6 rows. And also we can create the dataset by using table command like this. I think the believed is proactive. I think proactive is same as invisibility. No clock. I think it's the same. Okay, next the student t-test command. The explanation is same. Firstly, degree of freedom, the variance, and t value, calculate t value, calculate significance, and the result outcome here. This is our original created command. And also we can create the handmade Welch's t-test command like this. In Welch's t-test case, calculate standard errors using individual variances instead of pooled variance. That is the one difference. Numerator is here and denominator is here. And the degree of freedom is also different. In this case, in student t-test case, here, degree of freedom is very simple. Sample n1 plus sample size n2 minus 2. But in this case, we need to divide it by here using standard deviation. So this value is not always the integral. So the result would be a bit complex. And this is the significance and round because the result would be we should round the dataset because there is a lot of the 0 point blah 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 blah. It is difficult to interpret. So this command is these are one command run. After that, we check the mean, standard deviation, and sample size, then we get these statistics. So using these values, we can check the t-test result. Student t-test result is here, and Welch's t-test result is here. P-value is a bit different, and Welch's t-test would be more robust, but as you can see, the df, degree of freedom, is a bit different because there is such kind of calculation is applied only in Welch's t-test. But fortunately, student t-test and Welch's t-test is automatically carried out and run. This is the result, and p-value is here. P-value is 0.1007. Our handmade case, p-value is 0.0066, so this is the same. Almost same. And next is Welch's t-test automatic case. P-value is 0.101. Manually conducted, then this is almost same. And please check the option. Mischief, stroke, this is the group variable, this is the dependent variable, and data set, and this is the variance equal is true, then this is the option for variance. And if we designate the equal variance, then t-test conduct a student t-test. Other case, Welch's t-test is conducted like this. Val.equal equals false, or we write nothing, then this command run Welch's t-test like this. Welch's t-test result you can see. So basically this, if you want to conduct a t-test, this type t-test would be better. Okay, next. Next is a Mann-Whitney U test. This is equal the Wilcoxon rank sum test. The same test. This test and this test is same. And formula is here. This is used for in the case that our dataset is not normally distributed, because both the student and Welch's t-test assume our dataset follows the bell curve, the roughly normal distributions. If the normal distribution assumption is violated, we should use non-parametric test. This is the one example, one popular test of the non-parametric test. Mann-Whitney U test or Wilcoxon rank sum test. We do not assess the mean, but instead it rank all the dataset from smallest to largest, and then compare the sum of the ranks for each group. Then we get more robust result. The important thing is the rank all the dataset. So it is very strong for the outliers. Here is the pros and cons. The main advantage is robustness and fewer assumptions. It does not require the data to be normally distributed. So it's good for skewed dataset or data with outliers. It's also suitable for ordinal dataset. Rank the data so that it is good, also good for the ordinal dataset. Works with small sample size, suitable for ordinal data, and fewer assumptions. But there is the limitations. Statistical power, less efficient than t-tests when the data is normal. If data can be we can assume that the data is normal, then the t-test is efficient. Better fit. Then it means that require larger sample size for same efficiency. Statistical power will decrease. And interpretational limitations are here. Loss of information due to ranking. We rank the data, so some information has lost. It is almost same complex interpretation. Not simply there is differences in median values, but values for one group are generally greater or less than the other. That is the interpretation. And assumptions of homoscedasticity and independent sample requires 3 and 4 are required in the Mann-Whitney U test case. So, in other words, the result isn't a simple difference in means. Rank the dataset one by one, so the means information is lost. But we can get the one group are generally greater or less than the other. We can assess such kind of difference. Mann-Whitney U test in manual case is here. N1 equals some invisibility dark cloak equal cloak. N2 equals the same. N1 equal cloak and N2 equal no cloak. And add rank variable. Sorry, this is the typo. Visibility dollar rank is rank invisibility mischief. We rank the mischief values and compute U1 and U2 like this. Use summation. And this is the formula. R1 equals sum invisibility blah blah blah. Then we calculate R1 by summing the ranks only for the cloak group. R2, we do same thing to get R2 no cloak group. And U2 equal R1 minus N1 multiply blah blah blah. This is we apply the formula from the previous slide to get U1. This is same as U2. We calculate this one here. And finally, we calculate sigma U is here. This is the same as this one. We calculate, we want to get this sigma. So we calculate these and here, and finally we get here. Then we evaluate that z equals u1 minus mu u divided by sigma u. Then we calculate the z statistics by standardizing our u1 values. and p-value equals 2 multiply p0 minus abs z. This is finally we get the two-sided p-value from our z statistics using a p-norm function, which is related to the standard normal distribution. We apply the standard normal distribution and p-value, then we can print the final p-value. We can get the final p-value. This is the automatic way. Automatic way will Cox test and dependent variable, group variable, data, and in this case, exact equal false. Next slide, I think we explain this. If you don't use this option, you will not get any result when there are ties. Being ties is sometimes a problem, especially when the sample size is very small. We do this because our data has ties, which can cause sometimes problems for the exact calculation. Okay, this is the next test. So let's conduct the Mann-Whitney U test. This is the manual command. Compute n1, n2, and rank the variable, and compute u1, u2. Finally, calculate the sigma u and use the z statistics. Check the p-value. This is the I think row can be deleted. This is the Mann-Whitney U test. And the probability is the 0.1489889. And this is the Mann-Whitney U test automatic case. I think we can get the same result here. P-value is equals 0.1492. 0.14, a bit difference. There is a bit difference, but the basically same. So you can use the Wilcoxon test, this automatic command. But the inside of this command, inside of all the packages, there is the row calculation like this. Please remember that. Okay, next I would like to go to the Yuen-Welch's test. Yuen-Welch's test is the third alternative, and which is the robust and more modern way. It's called the Yuen-Welch's test, and the important point is the trimming. Trimming both ends of the dataset, usually 20%. This is the Yuen-Welch's t-test. It's robust against outliers because it's trimming, and robust against unequal variances. And here is the concept. First, trim the data. This means you remove a percentage like 20% of the highest and lowest scores, both groups. This throws away the extreme outliers, and then we do the calculations on the remaining data. Finally, we calculate a t-statistic similar to the Welch's test. But we use the trimmed mean and the adjusted variance and degree of freedom. In other words, this test's point is the Welch's t-test performed on trimmed dataset. Next slide is the formula like this. This slide is a bit complex. This is the math behind the Yuen-Welch's test. We can calculate like this, and I'd like to skip this point. And please remember the pros and cons for the Yuen-Stolymsky test. Robustness and reliability is the pros. The biggest pros is the robustness. The less sensitive to outliers because it trims the dataset. And like the Welch's test, it also handles the unequal variances very well. Resistant to violations of normality. And good control of type 1 error. And better performance with contaminated data. But there is some limitations. It can have reduced power with small sample size. We need to trim the data so the sample size is reduced. And the result depends on the trimming percentage you choose. For example, 10% trims or 20% trims, they are significant, possibly different. The significance possibly different. And the required sample size, we need to trim then the required larger sample size than traditional test. And like using this formula, then the a bit complex interpretation than student t-test. Okay, this is the command, and this is the for the first place. At the first place, we did Yuen-Welch's test by the automatic command. We use automatic command at the first stage. This is the dependent variable. This is the group variable. This is the dataset. This is the trim percentage. In this case, 0.2 means 20%. This is the result. Okay, we can check. Where is this one? Yuen-Welch's t-test. This is the WRS2 one. We can run some. And p-value is 0.16, so it is not significant. So all the test shows that these are not significant. There is no significance between the clock and no clock. And for example, we can change the trim ratio like this. And p-value and other stats are a bit different. Trimmed mean different 1.1, trimmed mean different 1. Yes, like this. And basically 0.2 is the general case rule of thumb. Okay, next I would like to explain the bootstrap multiply Yuen-Welch's test. Yuen-Welch's test is the robust but required larger sample size. So we can combine the bootstrap method and this test. This is a UMBT. BT means bootstrap. Mischief, Childa, cloak, data equal invisibility, and bootstrap is the 5,000 times. Like this. Okay, next we conduct UMBT. Then a bit time consuming. UN's test case, immediately we can get the result, but the bootstrap case, there is a small, a few seconds to calculate. For example, the bootstrap larger number, then it's more time consuming. And the result is here. Test statistics, p-value is 0.17. So basically same. And there is one. So basically same, and we can get the confidence interval. And this would be the robust way, because the bootstrap sampling and the original Yuen-Welch's way is robust for the outliers and uneven variance. Okay, this is the 3 examples of the difference test. Sorry, four examples of the difference test. Student t-test, Welch's t-test, Mann-Whitney U test, and Yuen's trimmed mean test, or with bootstrapping test. Student t-test is the most simple way. This is the classic way. It assumes normality and equal variance. It has the highest test power, but it requires the normality and the homogeneity, homoscedasticity. Next is Welch's t-test. It assumes normality but allows for unequal variances. It is generally recommended. And if the sample size is small and there is outliers, Mann-Whitney U test you can consider. It does not assume the normality, and it is based on rank. You should use this if the dataset is not normal, but some information like sample mean would be lost. The final is the Yuen's trimmed mean test. This is the robust option, and it is resistant to the outliers and non-normality. But it requires larger sample size, so sometimes we conduct bootstrapping at the same time. Okay, next, this figure is the summary. This is some flowchart which might be easier for us to follow. Let's trace the path for us to do the difference test. If, for example, first you test the normality, and if the data is normal, large sample and random, you then test the variance. And if the variance is equal, then you can use a classic student t-test. And normal and variance is equal, then you can use student t-test. Normal but variance are unequal, then you need to use the Welch's t-test. And if the dataset is non-normal, then you can ask outlier is a concern. If yes, outlier is problematic, then Yuen's trimmed test would be recommended. If no, outlier is not very problematic, you can use the Mann-Whitney U test. This is one example. And this is the Japanese version for Japanese students. And this is a basic strategy to assess the differences between the samples. Okay. So the next one is a few slides show the other test, cross-table testing and category test. For example, your dataset is in categories, not numbers, then you cannot use these tests. Mann-Whitney U test or Welch's T test and so on. In that case, you need to conduct the chi-square test or Fisher's exact test and so on. So I add this, right? The categories with 3 or more values. Then you can use the chi-square test and the classical Wallis test. The cross-table testing case, chi-square test and the Fisher's exact test can be done. And categories with 3 or more values case, classical Wallis test can be done. This is true. And how to conduct is here. Here is the minimal R code. First one is the classical Wallis test. And second one is the chi-square test. Third one is the Fisher exact test. This is for categorical variable. For example, group A versus group B, pass or fail, such kind of categorical dataset, then we can use these tests. And if the category is with 3 or more values, then we can choose the classical Wallis test. Classical Wallis test is basically the Mann-Whitney U test, but for 3+ groups. Okay. I would like to explain the final task for you. The final task uses the project star dataset as previous homework. Please write a report over 4 pages or more, including figures and tables. Big figure and big table is acceptable. And please include R code and chart. You may reuse any code and chart you have already created in previous homework. Analysis must include at least one figure and at least one statistical analysis. For example, the statistical test or linear or non-linear regression with diagnostics. For example, using QQ-plot or normality test or Leibniz test and so on, or checking skewness or equivariances and so on. And please write why you choose this statistical analysis and diagnostics result is here, blah blah blah. And you can add a lot of figures and more than 4 pages, including each figure and include R code. Add all R code at the end of the report. I need to check the R code. An additional point will be awarded for strong subsistence and exceeding the expected length with meaningful context. If your report is very interesting or very large and very good, include very good findings or interpretations I add one point. Okay, as for the AI use, these are the notifications. What arrows and not arrows are here. You may use AI to rephrase the sentences or interpret error messages or generate the command. For example, the generating, the revise the command and check the command, or helping your interpretation for the result. You can use the AI. But for example, the not allowed case, copying an AI-generated analysis pipeline without your own design, decision, or diagnostics. The fully use AI-generated command and document is not acceptable. Other case, the mostly produced by AI, text, code, table, figure that are mostly produced by AI, then it is not allowed. For example, it matches the result I can obtain by asking ChatGPT or Claude or something to compare the task end to end, and it is very similar, then I doubt that is AI generated. And absent special circumstances, the code is, for example, the code is unusually polished or diverges to very far from the course content, and explanations are overly advanced. If you are, it is, how to say, the context, the whole context are very polished and good, and AI code is also very polished, good, it's okay. But the unusually polished or the inappropriate case, please check. So I would like to say that please don't use mostly produced by AI would not be acceptable. Okay. Rephrase sentences or something are good. This is the example of my report. So please check this and create the final task, final document. Okay, that's all for the statistics class. Thank you very much for listening.